Good morning to my colleagues in Colombia. Thank you very much for the invitation to present here today. It is my sincere pleasure to be able to share with you some of Nmisa's experiences with supporting reliable testing in the agro-processing sector. My presentation will cover the following topics, starting with an introduction to Nmisa and the African Food Safety Network. Then moving on to how Nmisa is implementing metrological traceability through certified reference materials and proficiency testing schemes for priority organic food contaminants such as mycotoxins and pesticide residues. I will then conclude by touching on some of our future plans in this area. The National Metrology Institute of South Africa is a measurement institute mandated through the government's National Measurement Standards Act to support South Africa's global competitiveness through the provision of internationally accepted calibrations, measurement standards, and measurement services. We are funded through our National Department of Trade, Industry and Competition, and we work alongside our related technical quality infrastructure institutions to support trade through standardization, accreditation, compulsory specifications, and of course, metrology. I would like to provide a very brief history of NMISA. The organization was first established in 1947 as the National Physical Laboratory. As South Africa was a British colony, our measurement infrastructure reflected what was implemented in the UK at that time. The NPL performed calibrations for mass, length, and electrical measurements. And in 1956, South Africa received its first copy of the kilogram prototype, and only in 1964, after South Africa became a republic, did we sign the Meter Convention and formally changed over from imperial units to the SI units of measure. There have been a few name changes over time, ending with Nmisa in 2007. What may be of interest for the chemical testing community is that following the signing of the mutual recognition arrangement with the International Committee for Weights and Measures in the year 2000, Nmisa implemented a chemical metrology division. So this unit was established firstly with gas analysis, followed by inorganic analysis, and then in 2002 the organic analysis laboratory was established. In 2015, Nmisa embarked on the establishment of a reference materials program specifically to support the agricultural food production sector, which is the focus of my presentation today. Some interesting facts about Nmisa. We are composed of 23 ISO 17025 accredited laboratories, accommodating 186 staff members, of which 44% have postgraduate qualifications. Within the chemistry division, we are also ISO 17034 and ISO 17043 accredited for the production of reference materials and proficiency testing schemes. Our technical divisions are comprised of chemical, medical and materials metrology, physical and electrical metrology, applied metrology, and regional and international liaison and integration. One of the core focuses within Nmisa is to shorten the traceability chain for Africa, and we are best achieving this through our activities in AfriMets and the Africa Food Safety Network. The Africa Food Safety Network consists of mandated food monitoring laboratories in countries across Africa. This network was initiated through a three-phase IAEA-FAO technical cooperation project in 2012 initially, with only 15 countries, but expanding to 35 countries by phase 3 of the project. The main aim behind this project is to enhance food safety, consumer confidence, and to boost regional economic trade through the supply of safe and competitive agricultural products. Where the first two phases of the project focused on equipping laboratories and training, the third phase is focused on implementation, with the main project deliverables being an enhanced food safety regulatory framework, an expanded scope of proficiency tests and reference materials, enhanced national and regional residue hazards monitoring programs, and an expansion and harmonization of analytical techniques being applied by the laboratories, and increasing the number of ISO 17025 accredited government laboratories. The timing of this project coincides perfectly with the implementation of the Continental Free Trade Area Agreement, which relies heavily on competent food safety testing within the region. This free trade area will bring together all 55 member states of the African Union, covering a market of more than 1.2 billion people and $3.4 trillion US. But more importantly, we expect intracontinental trade to grow by 81%, of which roughly half will involve agricultural food production. The speed at which the CFTA was signed and ratified by the member states, roughly 4 years, reinforces the importance of this arrangement and escalates the need for African NMIs to enhance regional capacity to support testing required for agricultural production. This also implies improvements to Africa's food safety regulatory system. The African Union Commission is proposing an African Union Food Safety Agency, which would help with monitoring of sanitary and phytosanitary standards. These standards are informed by the FAO Codex Alimentarius, setting limits for food contaminants, and the Codex Committee for Africa, setting standards for uniquely African commodities such as cassava, fermented yogurt, and dried meats, for which the contaminant focus is predominantly mycotoxins and the application of veterinary drugs leading to antimicrobial resistance. Additional standards are informed by the different regional economic communities and existing food legislation at national level. Beyond Africa's borders, the regulations are determined by the respective food safety authorities of the export destinations. Enforcing these regulations rely on laboratories being able to produce reliable and comparable measurement results. The following slides will provide you with some perspective on the agricultural sector in Africa. It will provide an understanding of why this sector is so important and indicates the different measurement needs in different regions. The information here was sourced from several websites, which may also be useful in your own planning activities. What you see here is a heat map of Africa presenting areas in Africa with the most arable farmlands. And it is these areas where you would expect to find higher levels of agricultural food production. The most fertile areas are reflected by the red dots, where over 10 million hectares of arable land is available. Moving from South Africa into East Africa, Tanzania and Kenya, and across into West Africa, where we have Ghana, Ivory Coast and Nigeria, and then into North Africa, Morocco, Tunisia, Algeria. Of these fertile areas, it is interesting to note the percentage contribution to the national gross domestic product of these countries that originate from agriculture. The red dots here indicate where more than 25% of the country's GDP stems from agricultural food production, so predominantly running up the east of Africa and across into the west of Africa. Now, moving on to the next slide, it is important to also appreciate that in these red heat zones, these are countries where employment in the agricultural sector contributes to over 80% of the total employment in that country. Thus, agricultural food production is critical not only for trade, but also for job creation. Now, food safety testing for exports tends to be prioritized for most countries in Africa because of the revenue it brings to the region. From this heat map, over 1 billion euros in revenue is generated through agricultural exports to the European Union, largely from countries such as South Africa, Kenya, Ghana and Ivory Coast, Morocco, Tunisia and Egypt. Interestingly, most of these countries, specifically South Africa, Kenya, Egypt and Tunisia, have established chemical metrology infrastructures to support this trade. Trading agreements have already been in operation within the different regional economic communities, which are geographically divided into Southern, Eastern, Western, Central, and Northern Africa, where West Africa is predominantly French-speaking and East Africa English-speaking, while North Africa tends to form part of trade with countries around the Mediterranean Sea. Our next slides will look at typical agricultural exports from these regions, as this also helps metrology institutes to identify the services they would need to offer to support this trade. According to the World Trade Organization product classifications, our first slide highlights that Southern and Northern Africa are the largest producers of meat and products of animal origin to the European Union. In this area, there would be a larger focus on veterinary drug residue and pathogenic microbiological testing. For plant products, North Africa is exporting large quantities of edible vegetables, fruits, and nuts, along with Southern Africa. East Africa, as we know, predominantly supplies Europe with coffee, tea, and spices, while West Africa is best known for its enormous supply of cocoa and cocoa preparations. Critical chemical testing for these commodities would include mycotoxins and pesticide residues testing. Other significant agricultural export products would include oil seeds and preparations of vegetables, fruits, and nuts from North Africa predominantly, while the export of fruit juices and alcoholic beverages such as wine and beer dominates in the Southern African region. From a chemical testing perspective, mycotoxin and pesticide residue testing would be of concern, while food fraud and adulteration also occurs quite easily in these commodities. If we want to be able to compare measurement results within the free trade area, we will need to ensure that metrological traceability is established. The International Union for Pure and Applied Chemists have aptly stated, only measurements where the metrological traceability is established can be compared independent of when or where they were obtained. Now, establishing metrological traceability is not an isolated activity. There are several processes required to achieve this. You may find the comprehensive guide that is available through Eurochem and the International Cooperation for Traceability in Analytical Chemistry a very useful resource in your own laboratory. But within this guide, there is a detailed description of how to establish metrological traceability in the chemical lab, and this would include the use of validated analytical methods, appropriate calibration of equipment use, the use of reference materials both for instrument calibration and for bias assessment, the estimation of uncertainty of measurement, and most critically, the use of quality control materials and regular participation in proficiency testing to demonstrate that all systems are functioning correctly. Laboratories that are already ISO 17025 accredited will recognize these requirements within the international standard for the competency of testing and calibration laboratories. Now, realizing that metrological traceability is important along with continued participation in PT schemes to ensure comparability of measurements, Nmisa realized the importance of supporting critical food safety testing within the continental free trade area and therefore implemented an Africa Food and Feed Reference Material Program in 2015. The aim of this program was and continues to be to provide regionally relevant matrix reference materials and proficiency testing schemes. To identify and prioritize our activities within this program, we held several stakeholder engagements, and we also focused on the regulatory environment and typical challenges that countries were experiencing with agricultural exports and specific food contaminants. The chart you see here shows the European Union's Rapid Alert System for Food and Feed and presents a summary of border rejections, alerts and notifications received by Africa during 2017. And from this information, it is clear that we needed to focus on reference materials and PTs that would support measurements for mycotoxin analysis, pesticide residue testing, and for chemical content such as your antibiotic drug residues and artificial colorants. Each of these alerts potentially led to the loss of the product or a reduction in the market value for commodities in each country. In the process of wanting to produce metrologically traceable matrix reference materials, we realized that most critically we needed metrologically traceable calibrators in order to value assign the contaminants in the food matrix. At that time, there were no mycotoxin calibrators that strictly met metrological traceability requirements. Although Nmisa had been participating in core competency purity assignment comparisons to value assign neat materials, we needed specific training that would enable us to produce the ampuled mycotoxin certified reference materials. We were fortunate to participate in the BIPM capacity building and knowledge transfer program for mycotoxins in order to achieve this capability. We have since then gone on to produce the mycotoxin certified reference materials, and these capabilities are now listed in the key comparison database, which forms part of the mutual recognition arrangement for our national measurement standards at an international level. Our typical purity assignment approaches include the indirect assay of the main component applying the mass balance approach. This is achieved simply by determining the purity of the main component by identifying and quantifying all the impurities and subtracting from 100%. Structurally related impurities are determined by chromatographic and mass spectrometric techniques and other suitable detectors such as UV and charged aerosol detection. Residual solvents are screened by headspace GC time-of-flight mass spectrometry or flame ionization detection, while water content is determined by Kohl-Fischer coulometric titration and non-volatile residues by thermal gravimetric analysis. In the case of mycotoxin calibrators, the material itself is very toxic, only available in very limited quantities, and the traditional mass balance approach would therefore not be suitable as it requires significant amounts of material. The direct assay using the quantitative NMR technique was therefore implemented at Nmisa, and this was made possible through training received at the National Metrology Institute of Japan. Quantitative NMR allows you to directly determine the component purity, as the intensity of the NMR signal is directly proportional to the number of protons that are giving rise to that signal. So with the use of a primary reference material as internal standard to achieve traceability to SI, if you know the exact quantity and the number of protons that are generating the signal, it is possible to quantify the exact amount of substance of the analyte you wish to determine if you know exactly how many protons are generating the signal you wish to quantify. This is considered a primary ratio method, as it does not require calibration with the sample analyte that you wish to quantify. Our mass balance approach has been benchmarked through several international comparisons with other metrology institutes through the K55, the CCQM K55 Purity Assignment Series. With the QNMR technique only recently being applied on the determination of purity of folic acid and the CCQM K148A comparison for bisphenol A. Each comparison will reflect the complexity of determining purity of an organic substance that occupies a representative molecular mass and polarity space. So together with the BIPM capacity building program for mycotoxin calibrators, we were able to value assign the crystalline mycotoxin materials using QNMR and to gravimetrically prepare and certify the solutions. The summary presented here are for the QNMR value assignment of the aflatoxin crystalline materials. It is possible for high purity materials under well-optimized NMR conditions to obtain small uncertainties, as the main uncertainty contributors are mainly from the peak area integration of the signals obtained for the analyte and the internal standard, and the purity of the internal standard used. In our case, traceability to mass fraction amount of substance is obtained through the NIST primary standard PS1 for benzoic acid. The QNMR value assigned crystalline material was used to gravimetrically prepare the CRM solutions, which were then ampuled under dry nitrogen. Comprehensive homogeneity and short and long-term stability assessments were completed for these materials, including supporting purity checks by chromatography and mass spectrometry. Uncertainty contributions on the final certified values included uncertainty contributions from the purity assessment of the crystalline material, weighing and dilution processes, including a buoyancy correction, uncertainty, and additional contributions for uncertainty from the homogeneity and stability assessments of the solutions. Final relative uncertainties range between 2 to 4%. Our process currently involves using PT schemes as feasibility studies for the production of candidate certified matrix reference materials. In addition to this, of course, PT schemes are the indispensable tools for laboratories to independently assess the competency of their analytical methodologies. Within our region, the use of metrologically traceable reference values for PT schemes are critical, as there are a limited number of participants, or there may be several participants but having different experience levels, and therefore the use of consensus values is not recommended. To anchor the PT scheme performance from round to round, the Horwitz model is used for estimating the standard deviation of the PT. Nmisa is an ISO 17043 accredited PT scheme provider. Our materials are prepared with homogeneity and stability assessed according to these requirements. Our reference measurements are internationally benchmarked and typically apply ICP-MS, GC or LC-MS-MS. Through this process, we have gone on to certify matrix reference materials for aflatoxins in peanut slurry, maize, and milk, along with toxic and nutritional elements in wheat flour. There are currently mandated food monitoring laboratories from 22 countries participating in our regional proficiency tests. They participate in PTs for commodities that are relevant in their countries or as part of capacity building exercises. One of the first PT schemes we conducted in the region was for aflatoxins in peanut slurry. The reason behind this is because 15% of all European Union alerts, notifications and water rejections received by African countries have been for aflatoxins in ground nuts. It made sense to develop a PT scheme that would allow for measurements to improve in support of trade. However, further reasons to focus on aflatoxins included the need to monitor baseline levels of aflatoxin contamination in the region. Aflatoxins remain one of the most pervasive food safety challenges in Africa, not only through acute exposure leading to death, but also through chronic exposure to aflatoxin contaminated foods that find their way into the local African markets. Over 40% of commodities were shown to be over the maximum limits for food, and 30% of liver cancer cases have been shown to originate from aflatoxin contamination. Through the Partnership for Aflatoxin Control, PARCA, measures are being put in place by engaging with all stakeholders to find an integrated solution to this problem. To produce the PT scheme materials, both a blank and incurred sample batch was prepared. Whole peanuts were sourced and tested to contain negligible levels of aflatoxin. These were milled, mixed, packaged and distributed as a blank material to participants. Whole peanuts that were naturally contaminated with aflatoxin B1 and B2 were milled and mixed at a 1:1 ratio with double distilled water. The slurry was subsequently spiked with a predetermined volume of aflatoxin G1 and G2, acoustically mixed to achieve a homogeneous material, and then packaged. The materials were value assigned by UPLC with fluorescence detection using Nmisa aflatoxin certified reference materials. These calibrators were value assigned using Quantitative Nmr. The results from our most recent PT scheme round show large variation between the participants' results, ranging from 18 to 82%, when compared to the Horwitz prediction model of 22%. However, there was a marked improvement in the percentage of satisfactory Z-scores, which is a Z-score below 2, when compared to the 2018 peanut slurry proficiency test round, where the percentages were significantly lower. This highlights that the constructive feedback given to improve analyses provided in the reports and feedback presentations to participants has yielded the desired outcome, and we hope to see similar trends in measurement improvements and comparability for other proficiency tests over time. Another staple commodity consumed in our region is maize. The candidate material was prepared by sourcing 3 different lots of maize that was naturally incurred with aflatoxins, zearalenone, deoxynivalenol, ochratoxin A, and fumonazins. These materials were dried, coarsely milled, and then cryo-milled to a moisture content below 13% and water activity below 0.1. We ensured that the particle size distributions for each material were localized and below 500 micron before acoustically blending and mixing the material. The flour was packaged under dry nitrogen and irradiated before distribution. The certified calibrators were used for the final certification of aflatoxins in the material using a modified Zhang method, applying dilute and shoot UPLC MS. 39 laboratories participated in the Nmisa multi-mycotoxin in maize PT scheme in 2019. The results for aflatoxin B1 are presented in this chart, where the solid black line represents the PT consensus value, and the dotted black and green lines represent the 1 and 2 times standard deviation for the PT, using the Horwitz prediction model for expected variation between laboratory results of 22%. The error bars on each result reflect the uncertainties of measurement reported by the individual laboratories. What is interesting to note is the different analytical techniques applied by the different laboratories. These have been color-coded for ease of reference, and there appears to be good agreement between results regardless of whether the higher accuracy technique of LC-MS-MS isotope dilution is used or the more affordable and easily maintained LC fluorescence analysis. Satisfactory Z-scores were obtained by most participants for the determination of fumonisin, deoxynivalenol, and ochratoxin A. However, there were some specific challenges with zearalenone and aflatoxin G2, in particular, as the concentration levels were at or below detection limits for some of the methodologies applied. The next round for this PT will be held towards the end of 2022, and we look forward to similar improvements in performance as we did with the peanut slurry. As previously mentioned, our approach is to use proficiency testing schemes as feasibility studies for candidate matrix certified reference materials. So following PT schemes for the peanut slurry and for maize, where the short-term stability and transport stability conditions were assessed, these materials have gone on to be traceably value assigned for aflatoxins using the traceable Nmisa CRMs, and reference values have also been provided for other mycotoxins such as the fumonisins, ochratoxin A, deoxynivalenol, and zearalenone. We continue with long-term stability testing as per ISO 17034 and ISO Guide 35 requirements, and we are currently finalizing the matrix CRM for aflatoxin M1 in milk powder. Staying in the mycotoxin theme, within the African Union, the African Commodities Strategy aims to transform Africa from simply being a raw materials supplier for the rest of the world to a continent that actively uses its own resources to ensure the economic development of Africans. One example of a value-added agricultural commodity is the cassava plant, which may be well known to some of you and which has a potential far beyond basic human nutrition. For example, it has demonstrated health benefits in the animal feed industry, and the extracted starch can be used as a feedstock for a variety of industrial uses, including textiles and biofuel production. Within the Codex Committee for Africa, standards are being developed for cassava products. For human consumption, where contaminants such as mycotoxins and hydrogen cyanide have been highlighted, Nmisa therefore piloted a PT scheme for mycotoxins in cassava during 2020. The cassava flour was spiked with mycotoxins in much the same way that the peanut slurry was prepared. The material was then freeze-dried to remove solvents, acoustically mixed and packaged under dry nitrogen. The material was irradiated before distribution. Results for the aflatoxin B1, B2 and zearalenone toxins were satisfactory. However, challenges were encountered with the remaining aflatoxins, and no successful testing of deoxynivalenol or fumonisin B1 were made. Certainly, as can be anticipated, it was difficult for laboratories to fully validate analytical methods for these parameters in cassava, as there are simply no reference materials available for this commodity. To that end, Nmisa is embarking together with NMIs from Kenya, Tunisia, Ethiopia and Egypt to source and certify naturally incurred cassava products through a Pan-African quality infrastructure project. These materials will support the upcoming Codex Africa standards for cassava products. Moving on to the pesticides. Due to differences in growing seasons and pesticides applied, Nmisa is often approached by various agricultural growers associations in Southern Africa to assist with customized PT schemes that will be able to assess how well the export testing laboratories are able to test a proposed new European Union maximum residue limit for a particular pesticide or group of pesticides. We have conducted PTs since 2018 for diphenylamine in apples, for highly polar pesticides in plums and avocados, applying the European Union QP method, and most recently for multiple pesticide residues in avocado. A pesticide of particular concern was prochloraz, as it was banned from the end of 2020 for post-harvest usage, and new MRLs for pre-harvest usage is anticipated in 2022. Nmisa received organically grown avocados, and these were tested before spiking to have none of the indicated pesticides present. The pesticide PT materials are always distributed with blank materials to participants to assist with matrix matching where applicable. Care is taken to homogenize and stabilize the materials before shipping. Due to the nature of these compounds, the samples are usually shipped as frozen slurries. Through this customized PT, the South African Avocado Growers Association received sufficient evidence to support the testing capability of the export testing laboratories, and for prochloraz specifically, the Z-scores were satisfactory apart from the polar organophosphate acetate. All scores were satisfactory. And similar to the PT that we conducted for diphenylamine in apples, it is quite likely we will be incorporating this particular challenging pesticide in another round to determine if laboratories have implemented the necessary changes that would allow them to improve on their measurement results for this particular analyte. Nmisa PT schemes for pesticides in fruit are designed in such a way to match the crop growing seasons in the southern hemisphere and to also reflect the pesticides typically applied in the region. In cases where we see poor performance for a particular pesticide, constructive feedback and guidance is provided through the PT reports and sector presentations. These too lead to positive outcomes, as was the case for chlorpyrifos in peaches, where less than 40% of laboratories obtained satisfactory Z-scores. This analyte was subsequently repeated in oranges, and here 100% of participants achieved satisfactory Z-scores. To that end, Nmisa is currently finalizing 2 more matrix certified reference materials for maize flour and for cocoa powders for release in 2022 that will help laboratories to optimize their acid digestion processes. The Paki cassava project will commence during 2021, while a freeze-dried reference material for pesticides in plums or sweet peppers is currently being assessed for an Afrimets comparison for national metrology institutes and designated institutes in Africa. We are also planning the development of our reference measurement capability for heavy metals contamination in fish towards a new PT and matrix CRM, and hope to tell you more about these next time. In conclusion, I wish to acknowledge my co-authors on the work presented here, our colleagues at the BIPM, NIM China and the EU JRC Commission for the valuable training received, and the South African Department of Trade and Industry. Furthermore, Many thanks to our colleagues in the Africa Food Safety Network, especially Dr. James Asanya, the Technical Project Coordinator. I would also like to extend a warm invitation to everyone here to participate in our Africa Food Safety Workshop 2022. Due to the COVID-19 pandemic, we've had to postpone the on-site event, but we are looking forward to hosting it in Johannesburg, South Africa next year from the 27th of June to the 1st of July 2022. The main outcomes of this workshop is for industry experts to discuss a variety of food safety related topics and allow for networking between mandated food monitoring laboratories on the continent and our international experts. So of relevance to national metrology institutes would be discussions on advances in screening and confirmatory analysis applied to food safety testing, but also measurement standards such as our reference materials and certified reference materials, our interlaboratory comparisons and proficiency testing schemes that we are offering in our different regions. We would love to hear more about that from you, and we look forward to your participation. And finally, I would like to once again express my appreciation to the Metrocol organizers, the NMI Columbia, and to you, the audience, for your attention. I hope that you found the presentation insightful, and I welcome any questions that you may have. I thank you.